In this video, I will attempt to predict pressure and temperature. And what I mean by that is in the equation of momentum, we have the variable pressure, and we need to get dp dt to know how pressure will change. So at each time step, we can update pressure. So it's the new value at the current time. And additionally, knowing dp dt in the thermodynamic equation will give us dt dt, which is the temperature, which is also of interest, um, especially due to its effect on the weather. So in this, we will be using the um, equation of state, P equals rho r dt. And this equation is usually referred to as a diagnostic equation, diagnostic, which usually means it's not meant for prediction for the future. It's just meant to equate these two things at a current time step. However, I'm going to assume for this video that you can differentiate it, and I'm not 100% sure. I think that you can, even though it's diagnostic, and that's what I'm hoping. So there might be a better way of solving for dp dt, but we're going to do this way. This is all I know how to do right now. So you take the derivative in time of this, already comes out as a constant, and you have a derivative of rho t. You take the product rule, so product rule, and that will come out to this term right here. This is the product rule. For simplicity, or just how I chose to do it during the derivation, I guess to make the math easier, was to set this rho as anytime I had rho, I set it to alpha inverse, because just by definition, the density is equal to the inverse of specific volume. You don't have to do that. It just matches well with what I had written down for my equations. But we know from a previous video, according to the mass continuity equation, at the end I showed a partial rho, partial t, but you can also just add vection back, and you can, I think in the line before I showed this. So it's a rho, d rho dt. So that is equal to negative rho times the divergence, or rho times the convergence. Um, so, and I also took the rho and I took it out. So rho went here, and I of course switched it to 1 over alpha. So doing that, you'll get on the inside, the rho came out, this rho came out. You have rd over alpha times, in parentheses, total derivative of temperature minus temperature times divergence. Then we know the thermodynamic equation. So the using thermodynamic equation, we have dt dt is equal to 1 over cp dq dt minus alpha over cp dp dt. And we can plug this, which is this, here into here. And these two will cancel out. So we're left with this term again, minus rd over cp times this term again. Then we can multiply each side by cp over rd to cancel some terms. So these will cancel out, and this will cancel out, and this will cancel out, and then this will multiply here. So we're left with 1 plus cp over rd flipped dt dt. Since this term goes away, it's just t times divergence plus the Cp goes away. It's 1 over RD dq dt. And dividing this on both sides, we'll get that dt dt is equal to this constant 1 over 1 plus Cp over RD plus T times divergence, or I guess you could call this temperature divergence, um, temperature velocity divergence, not sure, plus another constant 1 over RD times the heating term, which, as we discussed earlier, this is like solar radiation, and also, I don't know if I mentioned, but it's called latent heat, L, like the heat that gets released during phase changes. Um, and of course, that is not, there's no uh, direct, like, closed equation for this currently. So currently they use like parameterizations and other ways of approximating it. So now we have an equation for temperature, yay, dt dt. So we started trying to get dp dt, it led us to equation for dt dt. Now we're back to trying to get dp dt again. So let's just plug this into this equation. So, the equation we had up here for P was this is equal to this. So that's exactly what I've written here again. And I switched back to using rho because in the end, I kind of decided I don't want to use this term. I want to just use rho, because density is, usually people calculate density, then they invert it to get this for thermodynamics, but you can really write either one, it doesn't matter. And so we have that equation I just talked about. Instead of RD over alpha, it's rho RD. And now we're like we know the temperature now, we know the density now, and we know the velocity now. And to get dp dt, we just need dt dt, and we just solved it right here. So we can plug that right in. So this would be the equation for pressure, and this would be the equation for updating temperature. And in the next video, I am going to summarize the fully coupled atmospheric equations, including the momentum equation, mass continued equation, moisture continued equation, this form of the thermodynamics equation, and how to update pressure. And after that, we'll see we have a system that we can constantly keep updating, and we'll always have the current information needed to predict the future. So stay tuned for the next video. Thank you.